You the symbols we were using without even writing down what they were. This was this Prof group, and then we had this Iwasawa algebra. And then there was the augmentation idea in there. And then maybe I'll also occasionally use this notation lambda n. I should have used it before as well, but I didn't, which was just lambda divided by nth power of the augmentation ideal. And remember, I was a compact closed ideal, and this nth power was just the algebraic nth power, ends up being the topological one as well. And then an was our notation for lambda n tensored with qp. This was a finite rank ZP algebra. We showed that. And this is, of course, a finite dimensional QP algebra. The consequence of our assumption on pi. And yes. So we had this map delta. I'm going to say somewhat more about it. That goes from A to A, completed tensor product with A, which by definition was the inverse limit of the AN's tensor AMs. And as I said briefly in words last time, of course, we could also just take the inverse limit of AN tensor ANs as well. Because taking the same index is cofinal in that whole double index system, so we may as well take that as well. And so using this delta, we had introduced a few objects. This delta made A into a complete Hoff algebra. I don't really need to explain what that is, other than casually in these lectures. So, right. Using that delta, what we did was we defined the group-like elements U. These were the G's inside A, such that delta of G is G tensor G, and epsilon of G is 1. Yeah, I forgot to remind you. I used this notation epsilon for the augmentation map from A to QP. This is the augmentation map. So that was the U. These were the group-like elements. And then, so this ends up being a subset of 1 plus the augmentation ideal, which the augmentation ideal as well. I'll remind you of that notation too. This was I mod I to the n tensor QP, and then take the inverse limit of that, so that sits inside A. And then there was the primitive element, which also is occasionally denoted P of A. This consists of those V in A, in the ideal IA, such that the delta of V is V tensor 1 plus 1 tensor V. These are the primitive elements. So this forms a Lie algebra. And this forms a group. Remember also there were these bijections, 1 plus IA goes to IA via the formal log, and the other direction exponential. These are both bijections. Okay, now, and these induced various other bijections that I'll remind you along the way, but let me first make some more remarks on delta, or another construction of delta. In order to say slightly more carefully these objections, address these objections that Peter Schneider brought up last time, I should say a few more remarks. Make a few more remarks. Very, very simple remarks, which I should have done it this way from the beginning, but I didn't, and then Peter raised those objections. Unfortunately, he's not here, but I'll reply to what he said now. So the point is that we could just start with our pi, and this is equipped with a continuous map to lambda m tensor n tensor lambda m. So there's this continuous map for each m. So this is just obtained by the map into the lambda sub n and then the lambda sub m separately. Of course, this sends it to G tensor G, the image of G tensor G. So of course, the image modulo I to the n and so on. But and this is a continuous map. I won't carry out the justification again. You can do it in the same way we did it for the QP version. And this lands inside the unit elements. It's clear because G is unit in here, and the other copy of G is a unit in here. And as was already pointed out previously, remember we were using these generators alpha I, which is AI minus 1. And the notation was that these AIs were elements of pi that form, these are bases in pi in the abelianization that when we go to the abelianization, these were the ZP bases. And we were using these elements before as generators for the ideal I, right? Now, it's a lambda module generators, left lambda module generators. And under this map, I already pointed out that alpha, of course, goes to, well, alpha I plus 1, tensor alpha I plus 1. That's where A will go, right? And then since it's an algebra homomorphism, minus 1 tensor 1. So that's what where this element will go. And that's, of course, alpha I tensor alpha I plus alpha I tensor 1 plus 1 tensor alpha I. So this lies inside the ideal. So with respect to that map, it lies inside the ideal I mod I n plus 1 tensor lambda m plus lambda n tensor I mod I n plus n. Which one am I doing here? M plus 1. So because of this expression, it lies inside the augmentation ideal tensor lambda on either side. Yeah? So if you take n plus m plus 1 power of this, then it will go to this ideal, yeah, to the n plus m plus 1. Because this is an algebra homomorphism, I forgot to say that. No, I forgot to say one other thing. Sorry, I got it all mixed up. This I should have written this here. Lambda induces this map. I just implicitly used without saying. This continuous homomorphism to the units will induce this continuous algebra homomorphism. And with respect to that, so this ideal goes to this augmentation, tensor products of augmentation ideal here. So this because it's an algebra homomorphism, these powers will go to powers of this ideal, but inside here this is 0. Because when you take the power, at least one of the factors will involve n plus 1 power, or the other factor will involve n plus 1 power. So this goes to 0. So this argument, some version I already gave last time, but I'm just repeating myself for the sake of clarity. So what we have is this family of maps, lambda sub n plus m plus 1 to lambda sub n tensor lambda sub m. So there's this family of maps. I'll denote these briefly by delta sub nm. Right? And I'll denote also by the same letter the A version. So then we get these maps as well. So remember, these are just obtained by here by tensoring with QP, and here everything is finite dimensional. We don't have to worry about any topology or anything. Right? And so taking inverse limits, therefore, gives us the map from A to A tensor A. So this is the delta again. But simply I was pointing out that the map itself can be viewed as just coming at this final level, from this final level, as an inverse limit. And I think I forgot to point that out last time. And the reason for saying this, now let's go back to the variety. Oh, actually, no. Before I do that, I'll just do one more thing. Okay, so that's the construction of delta. It comes as an inverse limit from finite levels. Now, one other thing. recall, last time we discussed that A together with the base point 1. This was the universal pointed pro-unipotent QP representation of pi. We proved that last time. John, did you have a question?
No,
Right.
trying to adjust my mind.
No, right, yeah. Pointed meant that it's equipped with a vector. Yeah? If you take, this meant that if you have any unipotent representation, finite dimensional unipotent representation with a choice of a vector, there's a unique map of pi representations from this pair to the pair. Maybe I'll just write it again. So whenever you have V with a choice of a vector V, and then rho is a representation, unipotent representation, then there exists, ought be, then there exists a factorization of this sort. It is a unique such thing.
And V needn't be finite dimensional.
I'm sorry?
V needn't be finite dimensional.
It can also be a pro-representation.
Be a pro-
Yes, pro-representation, right? But it's convenient to define it just using finite dimensional representation. Okay. But here, so this is a finite dimension. So in the definition here, we'll just take it to be a finite dimensional representation. But of course, it will have this universal property for other pro-representations as well. So this is the universal unipotent representation in this sense. Given any other one, there's a unique factorization through an algebraic map. Now, if you compare it with this picture over here, so we could ask, let me put this up. So A itself is a pro-representation, and all these A sub n's are finite dimensional representations now. So you could just take, if you just take the representation A sub n tensor A sub m, this will be a unipotent representation equipped with the vector 1 tensor 1. So this is a pointed unipotent representation. So according to this property, there exists a unique map from A to an tensor Am that takes 1 to 1 tensor 1 by the universal property. Right? Unique map of representation. And what is that map? Well, it's clear. It's just the projection composed with delta Nm that we referred to earlier. This is exactly what it is. This is the inverse limit of these guys, and we just constructed the delta Nm a moment ago. And the unique map from A to this tensor product representation that takes 1 to this vector 1 tensor 1 is exactly that map. And the reason is that this map delta is a map of representations because it's multiplicative in the group element. If you acted by a group element here first, then it would go to that group element acting on both vectors, so acting as the tensor product representation. And of course, that map is constructed to take 1 to this vector. So that's the unique one. There's a unique such thing. So this is the map that's given by the universal property. So that's one comment. Fred, you look puzzled.
Here's the meaning of the universal property. The one goes to V, right?
Yeah.
Oh, sorry about that. Let me explain it again. So I said this is the universal pointed pro-unipotent representation. So what this means is, given any unipotent representation of pi, there exists a unique algebraic map from U, algebraic representation of U, with the property that the vector 1 goes to V.
It's alt.
Sorry?
U goes to alt.
Alt V, yeah, that's right.
From A to V. You started with A and then
Alt 4.
Oh, so what did I say? Oh, yeah, sorry about that. Yeah. Oh, absolutely correct. Yeah, sorry about that. Not you. Yeah, no. This was because I confused two different statements. Thank you very much. Yeah, this is completely. Yeah, sorry about that. Given any unipotent representation, there exists a unique map of representations. That was the other unipotent completion property that the notation was confused. But, there exists a unique map of representations. A goes to V that takes 1 to V. That's the statement. Yeah. Thanks. Thank you very much. Yeah, map of pi representations. No. That was very silly. Okay, is this okay now? No. So that is the proper universal property of this representation. Now, there's that other group property floating around as well that I also stated last time. This is the property of the algebra considered as a representation. Now, therefore, for this guy considered as a representation, there exists a unique map from here to here that takes 1 to any fixed vector, but in particular to fixed vector, there will be such a unique map. And this is exactly the map we just constructed, just by the multiplicativity of delta. So that was a statement, which is here in a very complicated way. Furthermore, just one other remark in this general nonsense direction. Well, actually, there are many more remarks, but one other trivial remarks. If you consider this augmentation map, of course, it will take the element 1 here to the element 1 here, right? So it takes the 1 here refers to the group element given by the group element 1, and so it just, since you're summing the coefficient, it goes to 1. So if you think about this, this is a map of representations, and this will be, therefore, the map given by universal property for the trivial representation with vector 1. So if you take the trivial representation with just the choice of the vector 1, the universal property says that there is a map of representations again, and this augmentation is just it. That's what we're saying. So this is, as I said, all just completely general nonsense. But we have to state it once. But then the last remark in this line of generality is we could then ask, instead of that vector, suppose we change the choice of vector in any situation. Okay, but let me just illustrate it with this situation. If we took another vector, say for example, took the vector of the trivial representation and took any other element z, then again there's supposed to be a map, unique map from A to this guy, A1 to this guy, and it's obvious what it is, right? This has to be just z times epsilon, because that is a map of representations, and it will take 1 to z. That's it. That's the way it changes when you change the vector. Okay, now let's return to the geometry. So K is a number field again, and X over K is a smooth variety. And once again, I'm going to get this notation repeatedly confused, but I'm going to fix a rational base point that will also regard as a geometric point. I could keep using different notations, but whatever I do, I'm going to get it confused, so I'm going to give up and just use this one. Right. Now, the basic correspondence we discussed last time was that for every pi representation, D, there exists a sheaf V on X is a sheaf on the étale side in the étale topology, such that the stalk of V at B is canonically isomorphic to our representation V. There's this correspondence, right? That a functor going from representation to sheaves. Yeah? And it's in such a way that the stalk at your chosen base point is equipped with an isomorphism to the representation. Okay? So that's this standard étale topology business. And I'll remind you of this other fact that I mentioned that you have to think about once. I'm going to write down the careful proof of these constructions, but just say briefly. But remember, this construction was this associated bundle construction, to the principal bundle given by the universal covering. This sheaf was, and that fact is actually important when we discuss Galois actions. Okay. In particular, to these representations A sub n, right, we associated some sheaves, so this is our sheaf of QP vector spaces. On X bar. Oh, sorry. Again, confusion of notation. Pi here was pi 1 pro p of X bar, not X. So that's why to a pi representation we get something on X bar a priori, not on X. So there was this equivalence of categories. So to this particular representation we get this sheaf. And this was, of course, locally constant and unipotent. Which, remember, unipotent meant that there's this filtration by things so that the quotients are trivial sheaves or constant sheaves. And of course, that's because this representation has a filtration by representation so that the quotients are trivial representation. Trivial representation will correspond to the constant sheaf. Also, since this is an equivalence of categories, you get these maps, delta NMs, going from from the sheaf, A n plus m goes to A n tensor A m. You get these map at the level of sheaf. By the way, I think I may have written n plus m plus 1 by mistake earlier on one of the earlier panels. This should just be n plus n. This is the correct index. So this is what I want. All that preliminary was so that I could say this, because Peter Schneider raised the objection that if I want to take equalizers of maps between pro sheaves and so on, it's very complicated. So now we just have finite dimensional QP sheaves, and these maps are definitely standard stuff. Even that, I pointed out that the references are not so easy to find, but at least this is completely standard material. That's for finite dimensional QP representation. If you have a map of representations, you get a map of sheaves. So now we'll denote simply by A this pro sheaf given by the ANs, equipped with also all the maps between them as well, whenever n is bigger than m, which also come by functoriality of the construction. But for that pro sheaf, so that by itself is a projective system of sheaves, but I can still discuss its stock. When I write A sub x, this refers to the inverse limit of stocks of an sub x's. So when the A itself is just, we're not going to, we can't take projective limits in any reasonable sense. That's just a projective system of sheaves. But when we take the stock, we are going to take the projective limit. So this is going to be a compatible collection of elements inside the stocks at x of an. The question, Hannah? Sorry? Yeah, that's right. Lambda sub n was the p-adic sheaf, and this is the one with QP coefficient.
And so you tensor the p-adic sheaves, in the sense tensor. That's really the same as sheaves of that's
right. Yeah, there's maybe the terminology is slightly confused.
QP sheaf in the sense that it's a p-adic sheaf tensor that.
That's right. Yeah, that's right. Okay. It's a QP list sheaf in the SGA terminology. It's a list QP sheaf. And of course, the underlying foundation refers to all the facts that you just said. That there's this underlying ZP sheaf, and there's all these finite quotients and all this horrible stuff. But anyways, so the stock now we can just take. It makes sense to discuss at any point. The stock is just an inverse limit. And so if you look at those maps, we have delta sub n m. The stock at x is, first of all, there is a map from A plus A, the stock of this guy, to the stock of A n at x insert stock of A m at x. Okay? And so we can take the inverse limit of that, and we get delta x, which is a map from Ax to Ax completed tensor product Ax. So we get this map in any case. And I'm not ever going to use the map of sheaves, that's the point. I have a map of stocks in any case. So we don't have to write 50 more pages to discuss the map of sheaves. Oh, maybe I should have made one comment, by the way, here. If you, to get this map of sheaves, one needed the fact that I already alluded to, that the delta maps on the level of the representations is a map of representations, and we already pointed this out because delta is a multiplicative map, right? But the interesting fact is that there's no map of the other sort. There's no map from an tensor am to, say, whatever. There's no map in the other direction. Let me just put it this way. There's no way to construct a multiplication map. There's a co-multiplication map. Once you've sheavified, that survives because the original co-multiplication map was a map of was compatible with pi action, but the original multiplication map is not compatible with pi action. So there's no map in this direction at the level of sheaves. The stock at B still has that map, which is because that's the original representation, but at the level of sheaves it goes away. So this is a sheaf of co-algebras, this thing, in some appropriate sense, but it's not a sheaf of algebras anymore. Okay. So now the theorem, which maybe I already stated last time, I forgot, is that if you take A together with the element 1, what is this 1? It is an element of the stock at B. This is the universal unipotent, pro-unipotent pro-QP list sheaf. I'll use that terminology since the objection already came up. This is the universal such sheaf, pointed. Meaning, given any other such unipotent QP list sheaf on X bar, there exists a unique map from this one to that takes, with a trace of a vector that takes 1 to that vector. So let me say that. Suppose you have a QP list sheaf, unipotent. And suppose you choose a vector, maybe I'll call it u, so I won't get confused with inside this, right? Then there exists a unique map, right? F sub u from A to V, such that F sub u of 1 equals u. Map of sheaves. Okay, question? Oh, no, I can't. Okay. It's essentially locally constant. Remember, what it really means is that there exists locally constant finite sheaves and a projective system of such things together with maps from transition maps between them. Yeah? And that would be a Z-p-adic sheaf, locally constant Z-p-adic sheaf would be such a system inside some 2 category of inverse systems of such sheaf. And then QP list sheaf is just, you don't talk about the object, you talk about the category, which is the same object, and you tensor the morphisms with QP. But then, after you've done all that, you forget about it and pretend that this is just like the usual locally constant sheaves of QP vector spaces. In particular, when you take stocks, you tensor with QP. the objects. Okay, is that okay? This tensoring with QP at the level of stocks, of course, also can be functorially motivated. You're taking maps from QP to the inverse image of that guy at the pulled back to the geometric point, but taking maps inside this category of QP shifts. That's why you're tensoring with QP. So anyways, let me restate. This is the universe of such object. Given any locally constant QP shift, which is unipotent, and given any choice of a vector inside the stock at B, there exists a unique map from this shift theoretic map from A to B that takes your chosen element inside the stock of A at B to this other element you chose for B. Remember the choice of this vector, the point of it is that that's what gives the unique map. If you don't want uniqueness, of course, you don't need to choose the vector. Right. So I won't prove that theorem because that's exactly the same as it follows from the case that we did for representations. Right. But now, remember, if you're given any geometric point, say from spec k bar to x, it determines this fiber functor, fx, from sheaves to f sub x. So this, and I'm going to view this as a fiber functor from unipotent sheaves, QP sheaves on x bar to QP vector spaces. So I introduced this notation last time. This is the category of unipotent QP list sheaves. So this is a functor that just takes a sheaf. Oh, I already wrote it up here. It takes a sheaf to its stock at x and gives you a QP vector space. So this is a tensor functor with all these standard properties. And the theorem, which is just, again, continuation of general nonsense that you just once, and then forget about, is the following. If you take the hums from the fiber functor at B to the fiber functor at x, right? So this is canonically isomorphic to A sub x, our sheaf, the stock of our sheaf A at x. So these are the functorial maps of functors from FB to Fx. Inside the category of QP vector spaces, functorial maps from stocks at B to stocks at x, right? And you take this maps of functors, this is canonically isomorphic to the stock of A at x. So this is like the proof for universal covering spaces, but this one I will give again, because just to remind ourselves how this kind of correspondence goes. Without details, I'll just write down what the map is. Suppose you take a map phi from one fiber functor to another. So this is supposed to associate to every unipotent QP sheaf a map from the stock at B to stock at x. In particular, this will give us for each AN a map like this. So let's write phi sub AN. Supposed to give you maps of this sort in particular, right? Yeah. These are particular sheaves, unipotent sheaves. So there is such a map for every QP unipotent sheaf. So in particular for these ones, we get it. And then these are compatible over the ends, because that's what it means to be a map of functors. Between the map of sheaves, these have to be compatible. So these are
Just checking. The hum here was tensor QP.
No, it's just
no, it's not. It's before.
just hum
Which hum
in
is
the
hum?
hum in the sense of functors. So what does it mean? Remember, our target is the category of QP vector spaces, right? So hum automatically means that we have, for each object, we have to have a map inside the target category. So they're automatically linear. We don't have to worry about that issue. Now, all those things have to be thought through once, of course. That's right. But to have a map of functors means that indexed by the object of our source category, we get maps in our target category. So that's what maps of functors are. So in particular, yeah, so these are linear, and they're compatible over n's in the obvious sense that I won't spell out this time. So we can take the inverse limit. So we get phi, I'll write this as just phi sub a, that goes from a at b to a at x, the stock of a at x. So we can evaluate it at 1 now, right? So from here, we can take the phi a at 1, which is an element of a at x. So that's the map from here to here. Okay. Given a map of functors, we get an element inside this stock, yeah? In the other direction, again, it exactly imitates the case of universal covering spaces. Suppose you took an element A inside AX in the other direction. Suppose you take such an element, then we have to define an element phi sub a, right? We want phi sub a inside the Homs from FB to Fx. So what does this mean? I.e., that means that we want phi, oh sorry, I won't put this as a subscript, I'll put it here inside the bracket. We want phi sub a sub v for every sheaf v inside the category of unipotent QP sheaves. We want a map from v sub v to v sub x, of a functorial sort. So what is this object then? What is such a map? We just do this obvious game again and again. So to give such a map, we need to fix an element inside v sub v, and I have to tell you where it goes, right? But for that element, remember, there exists a unique map f sub v from a to v such that 1 goes to the element little d, right? By the universal property of our sheaf. So now define phi a sub v, phi a sub big V, the value at little v. Sorry, this is terrible notation. I should have used u here. Let me use u for the vector. I mean, all my notation is terrible anyways, but this was exceptionally terrible. So this, by definition, you can take this to be f of u, now evaluated at a, and this will be an element of v at x, right? Okay, so let's make sure we know what we're doing. So yeah, I first started with an element of the stock of a at x, of the universal sheaf at x, right? And I want to end up with a map of functors. To end up with a map of functors means that for each sheaf, I need a map from the stock of that sheaf at b, v, to the stock of that sheaf at x. So to say what that map is, I furthermore need to fix a vector of inside the stock at b, and the value of that vector, value of this map at that vector, how do we determine it? We take the universal map from the universal sheaf to v that takes 1 to that vector, right? And use the same map and just evaluate it at a. This is a map of sheaves. A was inside the stock of our universal sheaf at x, so this gives us an element of the stock of v at x. And this is the correspondence in the other direction. And it's boring to check that this all works, so I won't have the board. So that's the map in the other direction. So it's exactly like, so this same kind of construction works in every possible setting. So that's why we just did it once, did it carefully for universal covering spaces. But it works in this setting, it works for drum, local system, crystalline sheaves, and so on. It's the same. In other words, the problem of computing these kinds of Homs or automorphisms of functors and so on is always the problem of computing a good universal object that you can get some handle on. whether you're dealing with étale sheaves or representations, étale sheaves, connections, or crystals. Yeah.
Equivalence could exist without that.
Say again?
Such an equivalence could exist of this canonical automorph isomorph could exist without an universal automorph.
I need something to put on the right side. You can describe it. There are maybe other ways to describe it. But the one way to describe it is to construct a universal object. So, of course, there are other languages describing this whole process that you're constructing some adjoint to this other functor. That's what the universal object is. Well, if you write it down correctly, we're constructing the adjoint to the stock functor. Right. And now, the next theorem, which isn't completely general nonsense, it's fairly general, but slightly more specific than general, is that now we take the tensor compatible isomorphisms from FB to Fx. Not just all homomorphisms, but the tensor compatible isomorphisms. Yeah? And this is isomorphic to Px, which by definition is the elements in A sub x such that the augmentation map takes it to 1 and delta A equals A tensor A. So this now this is why, again, referring to the questions at the end of last time, the previous lecture. That's why I didn't want to do these delta shifts theoretically, and I don't need to, because I just need the map on the level of stocks, because this now makes sense without discussing any map of pro shapes, equalizer of maps of pro shapes. This is just a subset of the stock of elements satisfying this property. And this by is what I mean by Px, and these are exactly the tensor compatible isomorphisms from Fb to Fx. Okay?
So when you say tensor product compatible, you mean it takes tensor products?
Oh, right. So this notation, so let's explain what that means. Remember, if we take a phi, let's take an arbitrary isomorphism, okay, or even homomorphism from Fb to Fx. What does this do? This gives us a phi v from Fvb to Vx, remember, for every sheaf. So, well, even if it's an isomorphism, it's going to be an isomorphism. However, if we take two sheaves now, V tensor W, and take each stock at B, that's going to therefore go isomorphically to its stock at X via the map that phi associates to the sheaf V tensor W. Right? For every sheaf, you're supposed to have such an isomorphism. In particular, for the tensor product sheaf, it has to have such a thing. But because this stock is canonically isomorphic to the stock of V tensor the stock of W, both at B and X, there's another conceivable way to map this stock to this stock, namely the tensor product of the map associated to V and the map associated to W, which a priori doesn't have to need to have anything to do with this one. But this diagram commutes is what it means for this to be a tensor compatible isomorphism. That's the tensor compatible. That is the superscript tensor. The commutativity of this diagram. Okay, so let's prove this. Well, I'll sketch the proof. I'm terrible with using these boards, so I feel like I need to move it up and down every now and then. I'm not sure when is the best time, so I'm doing it randomly. Over the years, that's the most consistent negative evaluations I've had in my course. That my board work needs to be improved. Something like that.
I mean, that's the worst common feedback.
No, I didn't say it's the most worst. I said it's the most consistent. Worst, I wouldn't dare to share in public. Yeah. Right. So, okay, so let's sketch of proof. Well, essentially it's a complete proof, but I'll just say a little bit and say what's involved in completing it. Let's take an element of AX. Okay? And we know that there's this phi. We already defined this form corresponding to it. Okay? And let's check what it means for it to satisfy these two conditions. Okay, let's check what it means. So, first of all, so here's a lemma. But again, I should repeatedly apologize for the amount of general nonsense. But this general nonsense we're doing right now actually has some content. If you do this carefully enough, you actually get some results. The lemma is this. If phi A is an isomorphism, oh, sorry, the other way around. Which way do I want to do it? Yeah. If epsilon A is 1, then automatically phi A is an isomorphism. So a priori, remember, we just associated a homomorphism to each element. But if the A goes to 1 under the augmentation map, automatically it's an isomorphism. So that's one lemma. So let's prove this. So this is the kind of stuff, by the way, that you'll see in the Lin and Myun's article on Tanakian categories a lot of. Well, so let's take a sheaf and take an element U inside the stalk of V at B. And what we'll show is that we will show that phi A of U is not 0. So then these are finite dimensional vector spaces, so it has to be injective, therefore. Oh, sorry, non-zero element, of course. Start with a non-zero element. And so they have to be injective linear maps, so they're all isomorphisms. Now, there is this slight additional remark you have to make, that if these are all sheaf-wise all isomorphisms, then you also have an inverse functor. But that's obvious. It's defined to be the inverse at every level, but so we won't really go into that. But the inverse isomorphism, that is from fx to fv. But what you need to do is just check pointwise, that is sheaf-wise, that is injective, and therefore sheaf-wise an isomorphism. Then the rest follows. There's some theorem in MacLean's book about how that gives you the isomorphism of functors. Right. So what we'll do is we'll show that. How do we do that? We probably shouldn't be erasing this theorem, but anyways. Well, remember, V has this filtration. This is supposed to be some Vn, is Vn minus 1. V0 contains V minus 1 equals 0. There exists such a filtration such that Vi mod Vi minus 1 is just copies of the constant sheaf, some Ri. By this I mean the constant sheaf. Right. Now, since we chose a non-zero vector, so there exists I such that U is inside Vi, but is not in Vi minus 1. Okay? At the stalk at V, at B, sorry. It's inside. There's a smallest I inside which this is contained, at the stalk level, inside this filtration. Now we know that V, okay, so Vi will go to Vi mod Vi minus 1, which is now Qp to the Ri. and u is inside here, so this will go to something non-zero. Here. Right? So then taking one of its coordinates, what we find is, so from there exists an h from vi to the constant shift, now the shift vi to the constant shift qp, such that h of u is non-zero. Just take one of the coordinates of this projection. This is a trivial shift. We can find some map to the constant shift from vi, which is non-zero on u. Okay? Right. Now, one other remark is this. Since, say, vi is a subshift of v right now, right? Okay? So if we look at the stalks over here, so this inclusion is, of course, induced by a map of shifts. So now there's going to be phi, the map that phi associates to this subshift, right? vi, and the map that phi associates to v, that ends up in the respective stalks at x. So there are these inclusions. But this diagram has to commute, right? Because the map phi is compatible, in particular compatible with the inclusion of the subshift vi in v, right? So what I mean is that phi v of u is the same as phi vi of u, right? By the compatibility of this diagram. So we can compute phi v simply at the level of this subshift vi and forget about v. And on that vi, we have this map to this constant shift, which takes u to some non-zero element. So what we'll have is the following situation now. So vi at b will go over to vi at x via phi vi, right? And then this is going to go over to the constant shift, qp. I'll put the subscript v in there. And this is also going to go over to qp at x, which is also qp, of course, right? For the constant shift, the Stokes doesn't change. And there's also going to be a map from here to here, corresponding to the constant shift. So in other words, phi of qp is going to be this map. Right? But then this diagram has to commute because the map H was a map of shifts. Okay? Right. Now, but let's compute phi qp of what? Of h of u. Let's compute that. So remember, our element u is inside here, hu is down here. So let's try to compute this. How does one compute this? What we're supposed to do is we're supposed to take the shift qp and the element h of u, right? And then there's supposed to be a unique map from a1 to this guy, right? The universal such thing corresponding to this. I guess in the previous notation, this would be f of hu, right? There's supposed to be a unique map of shifts from a to the constant shift that takes 1 to hu. But what is it? We know what it is. This is hu of epsilon. That's what we said earlier, right? That's the only choice. When this is 1, this is our augmentation induced by augmentation map epsilon, right? And so if it's some other constant, it's just that constant times epsilon, because this is a map of shifts that does it, with the uniqueness. So that's it. So then we're supposed to take this thing. So therefore, phi qp of hu is supposed to be this map, f hu, evaluated at what? I don't know, I've lost track of what I was doing. Yeah. That element A. Okay. That's because I lost A in the notation. I'm working with phi sub phi A right now, right? I fixed an element A, and we're looking at the map of functors corresponding to that A. Phi here is phi A. phi is phi A. Sorry about that. So that's what it is. Yeah. But then, okay, now I'm I'm confused. There's too many diagrams, so so I won't get mixed up. Let me make sure I write down what I mean. However, now, so this guy, remember, is the same of H applied to phi A Vi of U. That's the commutativity of this diagram, right? Okay. But see, since this, we just said that this is just HU of epsilon A, right? That's what, because the map of sheaves is just a constant HU times epsilon. So this map is exactly HU, the constant HU multiplied onto epsilon, evaluated today. So this is of course non-zero. Because epsilon A is 1 by assumption. Epsilon A is 1 by assumption. Yeah. So this is non-zero, and therefore HU is non-zero. Oh, sorry, what did I, not HU is non-zero. No, here, H of phi U, phi A Vi, this is A here, I put the notation back in, of U is non-zero, yeah? And therefore, well, we wanted phi A Vi of U, which is also phi A V of U, this is non-zero. Okay, is this all right? We checked that some projection of it is non-zero, so the vector is not zero. Okay, so that's the calculus dilemma. Okay, now secondly, let's check the tensor compatibility. So the tensor compatibility of phi A, what does that mean? And now you can guess at this point. That's why I made this first that delta corresponds to simply the universal map of sheaves. That is to say, so if we look at the pro-sheaf A, of course, officially I should be arguing at all finite levels, but I'll omit that for a second. We can look at the pro-sheaf A and look at the pro-sheaf A tensor A. Yeah, and look at what phi A does to these two things. So first of all, phi A of 1, what is it? By definition, right? We're supposed to take the unique map from A to A that takes 1 to 1, right? Yeah, and evaluate it on A. But that's the identity map, right? Obviously, the unique map from A to A that takes 1 to 1 is the identity map. So this is going to be A, right? So this is an exercise in the definitions. To compute this for the sheaf A, we take the unique map from A to A that takes the universal element 1 to 1, which is the identity map, evaluated on the element A. That's A. Okay. Now what about phi A tensor A of 1 tensor 1? Let's look at that. Well, we're supposed to take the unique map from A to A tensor A that takes 1 to 1 tensor 1 and evaluate it on A, right? So that map was delta, remember, right? So this is exactly delta of A. That was what we checked for delta. So tensor compatibility amounts to the condition that delta of A has to be the tensor product. So when you evaluate tensor product of these two maps evaluated on 1 tensor 1, right? That is to say, tensor compatibility means phi A tensor A, yeah, equals phi A tensor phi A, right? When you evaluate it on one tensor 1, you get delta A equals A tensor A. So just forget general mathematics. So that's this condition. So what have we shown? Oops, did I get rid of the? Oh no, I didn't. What we've shown is that the map from AX to Hom FBFX exactly takes PX to the tensor compatible isomorphisms, right? That the right hand side does land inside the left hand side. And now to check the rest of the stuff, to see that this is a bijection, you have to work a little bit. And those are the details I'll omit. But the idea is, essentially we've shown, since every isomorphism there, every homomorphism comes from something in AX, right? We've essentially shown that the tensor compatibility condition always corresponds to this condition. The delta A equals A tensor A condition. That's already been shown. Now then the only thing you need to check is that epsilon A equals 1 condition. That's automatic once it's an isomorphism. If you know the coproduct condition, delta A equals A tensor A, and you know there is an isomorphism, so it might be 0. That's what the problem is. Yeah? But if it's not 0, once you know it's an isomorphism, epsilon A equals 1 is automatic formally from the identity. So that's the bijection. Okay, so that's the proof of the theorem. So I guess we're out of time. Okay, so I'm falling constantly behind, but I guess we should take a power break now.